Today, we are going to look at some of the applications of a couple of dirt cheap spectrometers. We are going to use them to extract some reference spectra from these glowing tubes of ionized gas. And then, we will use that information to try and identify what gases are inside various types of gas-filled tubes. Since the dawn of time, mankind has looked up and seen the effects of electrical charge as it ionizes gases into plasma. This could be both a source of awe and a source of fear. And even today, can be a significant source of risk. Personally, I find it highly amusing, especially when my human assistant almost soils himself.
Fucking hell.
Ah, primitive humans. Today, we are also going to use electrical charge to ionize some gases. Each one of these gases produces a unique color, composed of discrete energy levels, and results in spectral lines. And these lines tell the story of the subatomic structure of each of these elements. So, let's take an illuminating look into some excited atoms. Throughout this video, we are going to be using these two super cheap spectrometers to make all of our measurements. What we want to show is that just because these are cheap spectrometers, it doesn't mean that these must be crappy spectrometers too. They have their limitations, and so we will be building custom test fixtures and devising experiments that help to overcome any shortcomings that exist with these devices. We are going to be comparing our results with recognized test spectra data, and where there are differences, we are going to try and figure out why. And then, finally, we are going to do a little detective work. We have a small collection of tubes and bulbs, all of which will contain low-pressure gases of one type or another. We are going to see if we can figure out which gases these are, just with this spectrometer, and a bloody good dose of volts. These two small cheap spectrometers are really bloody useful, and a hell of a lot of fun to experiment with. But, they both suffer from fairly poor overall sensitivity. While the glow from these tubes might look pretty bright, especially when imaged through a sophisticated cell phone camera, and in darkness, the actual optical output is very low. Even this tube that contains neon, which is by far the brightest type we have, it really doesn't deliver a lot of optical illumination. So, we are going to need to find a way to couple as much of this feeble light into our spectrometers, and also to shield it from ambient illumination. We will use this lens to collect as much of the light from the tube as possible, and then focus it down to the input port of the spectrometer. We designed a little jig that we 3D printed. This holds the sample tube, the lens, and has adapters for both types of spectrometers, and even a webcam mount. This is a tiny, high-voltage AC power supply, and it only cost a couple of dollars. We have mounted this onto our test jig. The tube is energized through electrodes made from copper foil. There is a cavity for the tube to be inserted into, and when the covers are closed, there is a reasonable level of isolation from ambient light. When we power up the test fixture from a bench power supply, you can see that even with the test jig and the lens, the actual light emission is still pretty dim. This tube is filled with neon gas, and it generates the brightest glow of all of the samples that we have. We created some adapters to allow the light to be correctly focused into our spectrometers. We also made this adapter for a webcam. Here is the adapter for the little garden spectrometer. As usual, we will attach it with science-grade tack. And finally, there is this funky little adapter for the TLM2 spectrometer. This one is able to completely enclose this tiny little instrument. So, now that we have constructed a suitable test jig, let me introduce you to the things we are going to be testing. These tubes contain low-pressure gases. We have argon, helium, krypton, nitrogen, neon, oxygen, xenon, carbon dioxide, and air. Next, we have a small incandescent light bulb. The light bulb has a special gas filling. We are going to try and identify it from its spectrum. This is a mercury vapor lamp. As well as the mercury, there will be at least one gas present to help the lamp to start. Again, we are going to try and identify that. This is our favorite tube. It's a deuterium arc lamp. We have not been able to find very much data on this thing, so we have no idea if the deuterium is the only gas within this tube, or if others are also present. And then, we have a couple of Geiger-Müller tubes. This is a high-pressure sodium vapor lamp. We are pretty sure that there is a gas inside this to help it start, but we are not sure which. And finally we have a high-power xenon flash tube. We are not certain if xenon is the only gas used in this type of tube, or if there is a mixture. Hopefully we will be able to find out. There is one very important point that needs to be highlighted. When we bought these tubes, we received absolutely no data on them. The purity and the pressure of the gases within these tubes is completely unknown. This is very important, because which spectral lines that get excited within these gases is highly dependent upon factors like pressure. We thought it would be nice to first show the visible effects of the glow that each of these tubes create. We are using a fairly high-end webcam. It has a CMOS sensor with pixels that are larger than our old crappy cam. This means it has better performance in low light conditions. When the tube is energized, we get a nice image to record. In these kinds of low light conditions, even this 4K camera struggles to get a clear image. We have captured some reference images from Wikipedia, so you can see how our tubes compare. This is argon. Like most of our samples, it is a noble gas. As you can see, it glows with a color very similar to the reference picture. It isn't terribly bright, so the camera struggles to get a clear image. The next gas is neon, and it produces the brightest glow of all our samples. In fact, it is so bright that it can visibly illuminate the inside of our test jig. Again, we get a good color match to the reference picture above. This is helium, and it gives a result that we didn't expect. As you can clearly see, the color of the glow does not match the reference picture at all. We currently don't know why this is. If you do, please let us know in the comments. Krypton is another noble gas. It glows with a rather complex color. In general, the reference picture is a very close match to what we get with this gas tube. Nitrogen is the main constituent of the very air that we breathe. It has a distinctive pinky, purple color to its plasma glow. We will be seeing this rather striking color again very soon. Oxygen proved to be one of the most challenging gases that we tried to get to glow. Perhaps the pressure of this tube is just fundamentally wrong. Xenon is often used in flash tubes, which are known for having a bright white, short duration burst of light. Ours isn't that white, or even particularly bright, at least not in the visible wavelengths that this camera can see. This is carbon dioxide. We weren't able to find any pictures of glowing tubes to use as a reference. The color of the glow from this tube is visually pretty interesting. And finally, we have a tube of low pressure air. As you might expect, this gives a near identical glow to that of pure nitrogen. So, in total, we have 7 elements, 1 compound, and this tube, which is a mixture of gases. It was at this point that we had another idea for a quick experiment. We thought it might be good to see what other data can be collected with this webcam. Cameras like this are able to see quite far into the near-infrared band. All we need to do is to remove the short-pass filter from the camera. This is used to prevent infrared radiation from reaching the CMOS sensor. Instead of breaking this little standard lens, we switched over to a larger one, which we had already removed this filter from. Details of that project are linked in the description. On the front of the test fixture, we also need to add a long pass filter. This ensures that only the infrared energy is seen by the camera. As a demonstration, we can use another short pass filter to show that what the camera is seeing is only infrared light. This dichroic filter works by reflecting the infrared rays instead of allowing them to pass. Once this short pass filter is introduced, all of the infrared from the plasma is no longer visible. So, let's take a look at the infrared light, and put it side by side with the visible light we captured earlier. Starting with the tube containing argon, we can see very clearly that there is significantly more energy in the infrared part of the spectrum. In fact, there is so much infrared energy that it is actually saturating the camera image. Moving on to neon, we see a completely different picture. In this case, the visible energy is significantly brighter than the infrared light. It does help to explain why, back in the day, neon was extensively used in signage. And then we come to helium. Here we do have quite a lot of infrared energy, but clearly not as much as there is contained within the visible spectrum. Krypton, on the other hand, clearly has a spectrum that is disproportionately biased towards the infrared, and is exceptionally bright. Nitrogen also has a lot of energy in the near-infrared part of the spectrum, but the visible light also has a significant contribution to the total optical energy. Oxygen gives a very interesting result. We struggle to get any visible light from this tube, but in the infrared, we see a very different picture. Xenon emits a crazy amount of infrared when compared to its visible light. We will need to take some measures to prevent this from swamping the spectrometer results. Carbon dioxide gives almost no energy in the near-infrared band, but the captured video is rather pleasant to watch. As you might expect, the tube filled with low-pressure air gives almost the same results as we got from the tube of nitrogen. So, what did we learn here? Well, for a start, it is clear that for a few of these gases, we are going to need to take some additional measures when we try to make some spectroscopic measurements. Put simply, we will need to filter out the infrared if we want to be able to measure any visible light components. First, we are going to test our reference gas tubes, using the little garden spectrometer. Within our home lab, this is our main tool for optical spectroscopy. It's very cheap, and if you are interested, you can learn more about it in these 2 videos we made about it. Ours is a little battered now, but it still works just fine. First, let's take a look at the spectrum we get from argon. As you can see, the spectrum is dominated by lines in the infrared band. Looking at a reference spectrum for argon, we can see these strong infrared lines in the correct locations. We found a great source for copyright-free, reference spectra, called atomicspectra.net. Sadly, it looks like this resource is under threat from lack of funding. If you are one of those people that feels strongly about having free, online resources, you could always buy Julie, the lady that runs this site, a cup of coffee. Anyway, back to argon. It is clear that if we want to be able to see any of the visible lines, using this cheap spectrometer, we are going to need to first filter out the infrared. For that, we will use our visible light filter, which is inserted between the test fixture and the spectrometer. Okay, let's see what difference this makes to the measurement. Now, with the infrared removed, we can see another strong red line, right at the edge of the visible region. I suspect that if we were able to filter this out, we would see more lines in the visible region. Now, looking at neon, we can see that there is a lot of lines in the visible band. And comparing to the reference spectrum, we see a very strong correlation. Helium has a lot of lines in the visible region, and there is a good match with the strong lines in the reference spectrum. We suspect that the fact that ours glows white, but the picture on Wikipedia is shown to glow orange, is due to differences in the conditions in our tube. Krypton is another gas that shows very strong infrared lines, that appear to be drowning out the visible parts of the spectrum. So, we are going to need to try again, but with the longer wavelengths filtered out. Now, we see a very different picture, with the visible parts of the spectrum having lots of lines. Nitrogen, the main component of the air that we breathe, has a strong response in both the ultraviolet and the infrared parts of the spectrum, so we are also going to take a look with this filter. Immediately, we can see that the visible band is a lot more rich with lines of various colors. Oxygen was very challenging to get any kind of spectral data from. If you squint at the spectral plot, you can just about make out the two strongest lines, which are within the infrared region. Xenon is another of those gases that has too much infrared energy to allow this cheap spectrometer to see the weaker visible spectral lines. Again, we are going to need to filter out this infrared energy. And now, we can see a lot of spectral lines within the visible region. Carbon dioxide didn't give a terribly bright glow when ionized, but it does give some strong lines that appear to correlate well with a reference spectrum that we found online. Armed with this data, we can now go and do a little detective work. We have 6 gas-filled tubes that we are going to try and figure out the contents of. And just like a detective board game, it's a game of elimination. But, unlike a decent game of Cluedo, you won't get to give Miss Scarlet a good seeing to in the library with a candlestick. We are going to start off with this simple incandescent lamp. Here you can see, when we apply an electric field, the glow from the internal gas filling. Like all of these tubes, the glow isn't very bright, but it is enough to be able to do some spectroscopy, even with this cheap spectrometer. Looking at the spectrum, we can see that it is dominated by the ultraviolet and infrared energy. We could have used our visible filter to see into that band, but we felt that it was not necessary, as there was enough information to figure this out. We think that the two gases in this bulb are argon and nitrogen. This is a mercury arc lamp, commonly used for germicidal applications. We know that there is mercury inside this tube, but there should also be another gas, to help ionize the mercury when it starts up. The glow from this tube is rather beautiful. We know at least one of the contents of this tube is mercury, and here you can see all of the main lines are easily identifiable. Looking at the main peaks in the infrared, these have the distinctive pattern of argon. Now to look at the spectra from a Geiger-Müller tube. These are used in Geiger counters, and this type is sensitive to gamma, beta, and X-rays. It glows with an orange hue, so there are a few hints about the gas filling already. Immediately, we can recognize some of the distinct lines of helium. But there is clearly another component in this gas mixture. If we look at the reference spectrum of neon, then we see a very good match for our measured spectrum. This cool-looking tube is a deuterium arc lamp. It is used to generate a continuous spectrum of ultraviolet, and is used in lab-grade spectrometers. When excited by this weak electric field, it only gives a very dim glow. This is at the very edge of the sensitivity that we are able to detect. Our cheap spectrometer wasn't able to extract much of anything from this dim light. We had wondered if there was some amount of standard hydrogen in the tube, but there doesn't appear to be anything that we can see in the collected spectrum. Perhaps this is the deuterium alpha line. Or maybe it's just noise. This is a high-pressure sodium lamp. We are not going to be providing enough electric current to energize the sodium metal. What we are trying to see is the gas that is used to start the lamp. In the spectrum, we can see a series of very strong infrared lines. Based upon this spectral fingerprint, this gas appears to be xenon. One curious optical effect from the inner aluminium oxide tube is that it exhibits optically stimulated luminescence. Finally, we are going to test this xenon flash tube. Obviously, we know that this tube contains xenon, but we wondered if this was part of a mixture of gases. We have had this tube kicking around in a desk drawer for years. Perhaps it is time we used this thing in a project. Any ideas you might have for that will be gratefully received. The measured spectrum turned out to be less interesting than we hoped. All of the spectral lines that are visible are directly attributable to the xenon spectrum. Anyway, let's take a look at what this other cheap spectrometer can do. Whilst we consider the little garden device to be our main spectrometer, the TLM2 actually gets used a lot more frequently. It is just so convenient to use, it is small, easy to connect, and it comes with both a smartphone and a PC application. This means that we can use it, even in our favorite laboratory, which is down the pub. It is a well-known fact that most of the important scientific breakthroughs were made in exactly this type of laboratory. And before you ask, yes, we are those geeky guys in the corner of the pub. These two spectrometers have a slightly different performance envelope, so let me just explain the main differences. The little garden device has a slightly wider wavelength range and a much better spectral resolution than the TLM2. But the TLM2 has better wavelength accuracy, it displays in units of absolute illumination, and has far better matching of the illumination levels across the spectrum. But, to be fair, these are both fantastic value for money, given that they cost somewhere between $60 and $70. Moving to helium, we can see that the TLM2 managed to resolve some more lines in the blue and ultraviolet regions of the spectrum. If we look at neon, we can see that the little garden device sees a lot more discrete lines, many of which are just merged together on the TLM2. I could talk all day about the relative strengths and weaknesses of these two spectrometers, but in the end, it is sort of a case of 6 of one and half a dozen of the other. These are both excellent products, and you will be able to do some real spectroscopy with either of them. Hopefully, what this video has demonstrated is that cheap spectrometers like this are not just science toys. Some of you might be wondering where you can buy these devices from. Well, the little garden device is available on AliExpress. There is a link in the description. But the TLM2 is not so simple. If you are interested in this cute little product, then you will need to help me to convince the company to release this on Amazon. Currently, it is only available in mainland China. We get the feeling that the company really doesn't believe that there will be any interest in this product outside of China. And that is despite the fact that our video on this device got 86,000 views. So, if you are interested in this product, please send the company an email, asking them when it will be available to buy on Amazon. If enough people send them an email, maybe, just maybe, together we can persuade this company to release the product to the wider world. Anyway, let's see if a little sales pressure can get things moving. Spectrometers are awesome devices. They are the closest thing we have to a Star Trek tricorder. Take this Radiacode 102 for example. It is a gamma-ray spectrometer, and can tell you what isotope you are pointing it at. This KC761 does the same, but is more sensitive. And then we have optical spectrometers, which as you can see, will allow you to identify ionized gases. And finally, we have an X-ray spectrometer. Well, we would have, if we were able to afford one of these bloody expensive pieces of kit. These can be used to identify elements, and is the key component at the heart of XRF machines. Because of our geographic location, this company would not even quote us for this instrument, let alone permit us to buy one of these things. So, we have basically resolved to build our own. If that endeavor yields any worthwhile results, we will be sure to make a video about that, sharing the details. I think that the purpose of making this video was to show that spectroscopy is something that is available to everyone. Price is no longer a barrier, and with the addition of a couple of cheap filters, you can get results that can rival professional systems that cost 10 times as much. On this channel, we are firm believers that science experiments are something we should never stop doing. Everything we have done in this video, you can just look up on the internet and find the answer to, without the need for any DIY experiments. But when you have to work through the practical issues, and get your hands dirty in the process, the underlying principles become much clearer. And it is not like these kinds of instruments are hard to use. This TLM2 spectrometer even comes with a smartphone application. Using it is just a point-and-click process. From our own experiences of owning these cheap spectrometers, we can say that once you have it, you will constantly find new applications for it. The use case of spectrometers is as varied and diverse as the applications of light itself. Anyway, that's all we have for you today. We hope you enjoyed our little video, or at least found some parts of it interesting. If you think we deserve it, then please feel free to give it a like. And you could always hit subscribe, if you want to see more content like this. In a change from our normal practice, we have enabled YouTube advertising. We are saving up for a camera. All of the photography you have seen in our videos has been captured using a cell phone, the limitations of which is starting to limit the kind of content we can produce. We wish to express our sincerest gratitude to the following viewers for their donations towards our camera fund. This is still a hobby channel, So we can say what we want, and YouTube's algorithm can go and get f***ed. Thank you for your time.